Let's look at cylinder blocks. The cylinder block is the largest part of the engine. Its upper section carries the cylinders and pistons. Normally, the lower section forms the crankcase and supports the crankshaft. It can be cast in one piece from grey iron, or it can be alloyed with other metals like nickel or chromium. The iron casting process begins by making up the shapes of what will become water jackets and cylinders as sand cores, which are fitted into moulds. This stops these parts becoming solid iron during casting. Molten iron is poured into sand moulds that are formed by patterns in the shape of the block. After casting, core sand is removed through holes in the sides and ends, leaving spaces for the cooling and lubricant passages. These holes are sealed with core or Welsh plugs. The casting is then machined. Cylinders are bored and finished, surfaces smoothed, holes drilled and threads cut. All cylinder blocks are made with ribs, webs and fillets to provide rigidity, but also to keep weight to a minimum. As more manufacturers try to make vehicles lighter and more fuel efficient, more and more engine blocks are being cast from aluminium. A block made of aluminium alloy is lighter than if it were made of cast iron. So if two engines are generating the same power, the alloy version would have a better weight-to-power ratio than the cast iron version. Aluminium alloy blocks are made by various casting processes, including pressure casting. Another method is gravity casting, where the molten metal is poured into moulds. Cast iron liners are usually used in the cylinders of aluminium blocks, and sometimes in cast iron blocks. Some sleeves are cast into the block. Grooves on the outside form a key that stops any movement in the cylinder. They also increase the surface area to assist heat transfer from the sleeve to the block. Some blocks don't need liners. They can be made of wear-resistant material that makes a hard-wearing surface for the pistons and piston rings. Or the cylinder bore may have some sort of surface treatment to make it hard-wearing. When the cylinders, block and crankcase are all cast together, it's called a monoblock construction. This is called a horizontally opposed block. It has a split crankcase. The two engine blocks are joined together by the flanges of the crankcase. In air-cooled engines, the cylinders are usually made as separate parts, then bolted to the same crankcase. Each cylinder has cooling fins. They're often machined to give uniform thickness and allow free flow of air. This section examines cylinder heads. The cylinder head bolts onto the top of the cylinder block where it forms the top of the combustion chamber. Inline engines of light vehicles have just one cylinder head for all the cylinders. Larger inline engines can have two or more. V-type and horizontally opposed engines have a separate cylinder head for each bank of cylinders. Just as with engine blocks, cylinder heads can be made of cast iron or aluminium alloy. A head made of aluminium alloy is lighter than if it were made of cast iron. Aluminium also conducts heat away more quickly than iron. So with an aluminium alloy head, the heat of combustion can be conducted away into the coolant more quickly. Manufacturing the head is similar to manufacturing the block. A casting mould is made. Sand cores are put in to form any hollow areas. Depending on the engine, these can be for coolant and lubricant passages and inlet and exhaust ports. Air-cooled engines have cooling fins cast into the cylinder head. The underside of the head is shaped to form the combustion chamber. Molten metal is poured in and allowed to cool. The cores are broken out and removed, and the cylinder head cleaned of any sand. After casting comes machining. Surfaces that must seal are machined flat. Holes are drilled and tapped for attaching bolts and studs. In sand cast heads, the large holes that had contained sand are machined, then fitted with soft metal plugs called core plugs. Cylinder heads are designed to help improve the swirl or turbulence of the air-fuel mixture and prevent fuel droplets settling on the surfaces of the combustion chamber or cylinder walls. When air-fuel mixture is compressed between the piston and the flat part of the cylinder head, it produces what's called squish. That means squeezing of the gases to increase their velocity and turbulence. In petrol engines, the three most popular combustion chamber designs are called hemispherical or pent roof, bathtub, and wedge. This is the hemispherical or pent roof combustion chamber. It has the intake valve on one side of the chamber and the exhaust valve on the other. This provides cross-flow. Air-fuel mixture enters on one side and exhaust gases exit on the other. Positioning the valves in this way leaves room for relatively large valves and ports, and that helps the engine breathe. Breathing refers to the engine taking in the air or air-fuel mixture. Fuel starts to burn at the plug. Then burning travels outward in all directions. This is called flame propagation. With the plug in the middle of the hemisphere, the flame front has less distance to travel than in some other designs. This gives rapid and effective combustion. This design is common in a lot of passenger vehicles. The bathtub combustion chamber is oval-shaped, like an inverted bathtub. Valves are mounted vertically and side by side, making them simple to operate. The plug is to one side, and that creates a short flame path. It all helps increase turbulence. The wedge-shaped combustion chamber tapers away from the plug, which is at the thick end of the wedge. The valves are in line and inclined from the vertical. This design usually has a smaller surface area than the others, with less area where fuel droplets can condense. Less fuel is left unburned after combustion, which reduces hydrocarbon exhaust emissions. And since the flame is directed towards the small end of the wedge, damage caused by detonation is reduced.